Net force equals negative kx is a linear restoring force. Characteristics of mass on an ideal spring. Or a pendulum, low amplitude pendulum, abbreviating that. Okay, so we have this relationship for an ideal simple harmonic oscillator, it turns out, because that's what these are. And we're going to see what we mean. We're going to see here exactly what we mean by simple harmonic motion. We won't learn to solve a lot of problems, but we're going to get a framework here. So, net force, of course, by Newton's second law is mass times acceleration, and acceleration is the second derivative of position with respect to time. So, setting this expression for the net force equal to this expression for the net force, we get this equation. We divide both sides by m to isolate the second derivative of x, and we put express x as x of t, emphasizing the fact that x is a function of t, here and here. Now we can leave off the t and leave it as understood, or we can put it in if we want to be really explicit about the fact that x is a function of t. But whether it's written this way or this way, it is considered to be a function of t. Okay, now this then says that x of t is a function whose second derivative is a negative multiple of itself, because negative k over m, k and m are both positive quantities. So negative k over m is a negative quantity, so that the second derivative of x is a negative multiple of x itself. Well, what kind of function could x of t be? This is kind of limiting. There aren't many functions whose second derivatives are negative multiples of themselves. In fact, there are only really two types of functions, two functions that satisfy this, or one type of function if you use Euler's identity, and you don't know what that means, but I'll probably mention it before we're done. Okay, so let's try some different functions just to see if some functions are multiples or negative multiples of themselves. Now, the functions that, exponential functions, and the question I asked in class is just what kind of functions do we know how to take the derivatives of? Well, obviously exponential functions, logarithmic functions, power functions, trig functions were mentioned, hyperbolic trig functions, and of course then rational functions, and when rational functions was mentioned, I threw in polynomials. For some of these, it's going to be very obvious that this condition doesn't hold. Actually for most, but let's start with the exponential function. Now, I used k here just because I kind of reflexively do that, and that was kind of unfortunate because I used k here. This k is not the same as this k, so I'm just investigating functions to see what functions, how the second derivatives of various functions behave. So if the function is a e to the kt, which is a general form of an exponential function, then the second derivative is k squared a e to the kt. Chain rule gives us a k for each derivative out in front. Okay? Well, that's a multiple, but not a negative multiple. So we're close with the exponential function. It turns out that we actually can hit the nail on the head here. Now you can store this away. I did mention it in class also, that if k happens to be an imaginary number, then this does satisfy. Okay? Okay, well, we tried natural log of kt. Its derivative is just 1 over t ultimately. And I'll just make a quick side note there that natural log of kt is the natural log of k plus the natural log of t. K being a constant, the natural log of k is a constant. Its derivative is 0. The only thing that has a non-zero derivative would therefore be the natural log of t. And we could reason out that this is then 1 over t without even going to the chain rule, but I use the chain rule here. So it's k times, that's the derivative of kt, which is k, times 1 over the quantity kt, and the k's divide out, you still get 1 over t. Okay, and the second derivative would be negative 1 over t squared, so this is not even close. This second derivative is not even a multiple of the original function, as was the case where the exponential function, the derivative, was a multiple of the function. It just wasn't a negative multiple, again, unless k happens to be imaginary. Well, next thing was suggested was sines or cosines, and we hit the jackpot there. The derivative of sine of kt is k cosine of kt. The derivative of that is k times the derivative of cosine of kt, which is negative k sine of kt. We get negative k squared sine of kt, and that is a negative multiple of the sine of kt, provided k is a real number. It turns out that an exponential of an imaginary is a combination of sines and cosines. So this thing where if k is imaginary, in fact, gives us the sines and cosines, and that's by the Euler identity. And I'll just write that down. It says e to the I theta equals cosine theta plus I sine theta. If you haven't seen this before, especially if you're in engineering, and if you're going to be taking differential equations, you kind of want to get this. If anybody wants me to explain this, I'll be glad to explain it. It's real easy to explain in terms of power series, which is something you should have covered, I think, in first year calculus, to a sufficient degree to understand this. Okay, now, same is true for cosine. You can do this yourself. Second derivative of the cosine of kt is negative k squared cosine of kt. So we've found at this point that a sine or cosine function has a second derivative that's a negative multiple of itself. It's going to be true for any sine or cosine function.